Greetings, geometry students. It's time for lesson 8.4. Today we're learning about similar triangles and also about the angle-angle similarity postulate. That, among other things as well. And so make sure you're using those extra examples in your book, and let's get right into it we're going to start off with the angle, sometimes called the AA similarity postulate. It's a postulate because we're just going to assume that it is true. We're going to start with this as our base, as our foundation for talking about other things about similarity with triangles. This is postulate 25. So just like before, we had angle, side, angle, 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 side, 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 angle, side, and hypotenuse, leg with congruent triangles. Similar triangles, we have this new one. We have angle-angle similarity postulate. So it says this is true. We can assume this is true. If not true, but if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And so I know we defined this or wrote this down off to the side on the previous lesson, but I just want to really make sure you got it down in a different color. I want you to write that means similar. So the single squiggly mark, the tilde, is meaning similar. And let's check out a first example where that's the case. We could also, before I move on, we could also say that by the third angles theorem, that's a theorem we should remember from a while back, but if you have two angles congruent to two angles in two separate triangles, you can prove that the third angles are also congruent to each other. So angle-angle is kind of like angle-angle-angle. You could actually prove all three angles if you can prove two, but we're just saying all you need is two. Yeah, we could prove the third ones are congruent as well, but you just need two to start with. So let's say in the picture that we're about to draw down here in the picture, triangle ABC is going to be not congruent to, but is going to be similar to triangle ADE. So let's draw our triangle. It's going to look something like this. It's kind of a long, skinny one. And then I want you to draw something, a line, a segment over here that is parallel to this part right here. So that parallel to that. Okay, and we're saying that's the same there and there parallel wise. And let's put in some markings on this picture. This is A, this is B, this is C. I'm sorry, that's not C, that's D. This is going to be C down here. So here's triangle ABC. Triangle ADE is going to be the bigger one in the picture. And we're going to say that CE is 10, that BC is 6, that that's 101 degrees, and that all the way from A to E is going to be 25. And we're going to learn, within the context of this example, some other phrases, important definitions of things. This is one thing you definitely got to know what it is. A statement of proportionality. A statement of proportionality. What is a statement of proportionality? It's a statement that states things are proportional in a certain way. So think about what it sounds like, what it might mean. That is what it means. So it's a statement of proportionality. It would be comparing similar parts to each other. So the long part in this smaller triangle would be properly compared to the long part in this bigger triangle. So AB over AD would be a good comparison from small triangle to big triangle. You could also compare this horizontal part AC to AE, small triangle to big triangle, parts that match up. And then finally BC, small triangle, to DE would match up as well. So this is a statement of proportionality. And let's box that in, and then in your different color, I want you to write here that these top values are going to be, or that they are, the bigger I wrote bigger originally, I meant smaller, so sorry, just a moment, the smaller triangle values. And so down here, the AD, the AE, the DE, that's the bigger triangle values. So it has to stay consistent. You have to keep comparing the same things across all the way. You can't have bigger here and then smaller here and then flip-flop it and say that those two are equal to each other proportionally. That doesn't work. So you got to keep the same values all the way across. On the bottom, we've got bigger triangle values, and on the top, smaller triangle values. Okay. And another way, before I move on to the next part, another way you can compare that is by looking at the similarity statement itself up here. So AB, the first two letters, should match up with the first two letters of this one, AD, and it does. AC, first and third letter, should match up with A and E, first and third letter, and it does. BC, the last two letters, should match up with the last two letters here, DE, and it also does. So those are two different ways. You can look at the picture, or you can look at the similarity statement and decipher that from there. Part 2 to this, example 1. If I asked you to find the measure of angle D, what would you say? So since you have a triangle here that's similar to the triangle here, that means this angle, the measure of angle ABC, would have to match up with the measure of angle ADE, which is the same thing as D. Since D is the only letter here, we don't have to use three letters, we can just use the one. But I would have to use three letters for this one, because saying angle B isn't clear if it's this one, or the whole angle, the whole straight angle there. So measure of D would equal the measure of ABC, which equals 101. So if I asked you to find what the measure of angle D was, you would say 101 degrees. And for 3, let's say I asked you to find DE. So that's what we're going to do on this last part 2, example 1. Find DE. So what could you say? You could use the similarity statement that you've already written out and look for parts that you know already, parts that you have. So AC and AE, do I know both of those? Because I know I want to solve for DE, so I'm going to be missing that part. But let's see, do I have AB and AD? I don't have any of those. But do I have AC and AE? Well, I know AC is going to be 25 minus 10 based on what's there. It would be 15. And I know that AE, the whole thing is 25. And so it looks like I have the fraction here. This is 15 over 25. BC is 6, and DE I could call X. So why don't I do that up here? I'm going to call that X. And why don't I actually leave that out? Could you call this X? Could you label it like that? Yeah. I'm going to show you what else you could do. So you could say that AC over AE equals BC over DE. Where did I get that from? I got that from my statement of proportionality. And so this would imply that AC, we're having 25 minus 10 there. That's where that comes from. So it's the whole thing minus this part is what you're left over with here. And then AE is 25. That's equal to BC is 6. And then instead of writing X, you can just write DE. So we saw that before. Excuse me, we can leave it like that if we wanted to. If you wanted to write X instead, you could do that later too. Notice I put parentheses around this because that's going to be helpful when I'm thinking through this. And so I can simplify this. Why don't I do that before cross multiplying? And so I'll do that in my next step. You can do this underneath here. I'm just out of space here, but I wanted to keep it on the same page. So I could say 15 over 25. This would be the same thing over here as this. It's 6 over DE. And now different color will cross multiply here and here. and we can say that 15 times DE, which you could write as 15 times x if you had x there instead, is 25 times 6. That's 150. If you divide both parts by 15, you've got your answer. DE equals, this will cancel here and here, this would be 10. Left over with 10. Right, so let's move on to a second example. In this example, are the following similar? And so let me pause the video here for a moment. I'm going to draw in some triangles and have you copy those down. And remember, with this kind of stuff, with similar triangles, congruent triangles, saying that shapes are exactly the same or similar to each other, you can't assume based on the looks. I tried to draw both of these so that they looked like they were similar, but we're going to trust the information given in the picture to see if that is actually the case. Let's say that this one is 50 degrees right here, this angle is 50 degrees up here, and that this one is a right angle right there. So a 90-degree angle right there. Over here, we'll label these with some letters. We'll say this is S up here, R down here, and T here. This will be P, M, and Q. RS 16, RT 12, ST 20, MQ 15, PQ 26, PM 20. And we're going to say that this angle and this angle are congruent to one another. So are these similar? Are they going to match up? So let's check it out and let's see what we got. What could we do here? In this picture, could you add another piece of information here? Let's do this in a different color. If this is 90, what can we do right here? We can say that that is 90 as well. That is all you need. If you have two angles here and here, we could do this. We could figure out this is 40 based on they add to 180, and that would be 40 as well. So you have all three angles, but remember, you just need two to compare. So angle matches up with angle. I don't need to know anything about the sides to compare similarity. I just need to know angle matches up with angle. That's all I need. So this one I would say yes by angle. So the angle similarity postulate, it's actually a postulate. We can just say AA and I'll know what you're talking about. Okay, and on this one, are they going to be similar to one another? And so do we have the angles here being congruent? No. I'm going to excuse me, I'm going to not include any of these other angles. So you don't know. They might be. This angle could be the same as this angle here. It looks like it is, but we can't assume that they are. So it looks like on this one we're going to need to check if the sides are proportional. So are these sides matching up with each other? So let's see. RS would be a good comparison. So let's compare RS to, RS would match up with MP. So R to S matches up with M to P. So let's see what that is. As a fraction, that would be 16 over 20, which would equal 4 over 5. And now let's compare another one and let's see if we get something the same or different. So I could compare RT to MQ. Looks like that would be 4 over 5. But let me see if I can get one that's not. So this looks like it's got some potential here. This looks serious. This is scary here. I'm not sure. So TS compared to QP, what does that equal? That is 20 over 26. Uh-oh. If I reduce that, I get 10 over 13. Clearly not the same as 4 over 5. So are sides proportional? No. How many sides have to be proportional for similar shapes, similar polygons, similar triangles here in this instance? They all do. Since these are not equal to each other, this does not equal that. Let's write that down. Since 4/5 does not equal 10 over 13, are these going to be similar to one another? No. So they are not similar. And then in parentheses, let's write that sides, all sides, that's a better way to write that, all sides must be proportional. So they are not similar. And parentheses, there we go. And then just want to make one more note here, and then mention something about an example in the book that I would like you to read, and we'll call it a day from there. So just as with perimeters, so we saw theorem 8.1. Theorem 8.1 said that the ratios of the sides should match up with the ratios of the perimeters, or it will match up with the ratios of the perimeters. That was from 8.3 here. Here it is, theorem 8.1. Two polygons are similar. The ratio of their corresponding sides equals the ratio of their perimeters. And so just as with perimeters, you can also say this with any two similar polygons, the ratio of any two corresponding lengths. So any two corresponding lengths. And then I'll say e.g., for example, is what that stands for. E.g., for example, altitudes, which would be heights, another word for heights. Altitudes, medians, those things connecting the midpoints from one midpoint to the opposite vertex. The medians, diagonals, etc. is equal to the scale factor of the polygons. And then please write this note underneath that. So I want you to do this right now too. So we're not going to do an example, but it's going to assume that you're going to look at this example in the book for me. So look at example 5 on page 482 to see an example of this. So do that right now. Make that the last thing you do here. Check out your book, look at that example, and see that. And I will show you quick what I would mean. Let me bring up an old drawing here from one of our finished lessons here. Yeah, I'll go to 8.2. So this would be saying, I'm not actually going to draw this, or I don't want you to draw this in your old notes, but saying if you found the altitude here and you found the altitude here, if these were similar shapes, if this big triangle were similar to this one, yeah, the perimeters would all be similar. It would also be true that the heights, the altitudes, should be similar as well, ratio-wise, or one fraction to another fraction should equal the same thing as the ratio of their perimeters and the ratio of each individual side. And so that'll do it for us for this lesson. Back to 8.4 there. Just check that out. Make sure you understand that. Read that over a couple times if you need to. Go back and rewind, refresh, renew your mind, and I hope this helped. We're all good. Okay, 8.4, all set to go.